Number 10, if football is kicked off the ground at a distance of 50 yards downfield, neglecting air resistance, which of the following statements would be incorrect when the football reaches the highest point? Okay, in this class, we've talked about some situations. And one of the situations would be, what if we fired something straight up in the air? And if we do that, then when it gets to the top, it stops and then it comes back down. But that's not what's going on here. What's going on here is we have a football that's kicked and it has both an X component and a Y component. So when it gets to the top, it's not at rest. It still has a vertical component of velocity. So let's take a look. All the ball's original kinetic energy has been changed into potential energy? No, that's not true, because it does still have kinetic energy. So no. The ball's horizontal velocity is the same when it's lifted. That is true. We've talked about that the the horizontal velocity stays the same the whole way. The ball will have been in the air 1/2 of its total flight time. That's probably true. When it gets to the top, that's about halfway. The vertical component, and I say probably because it really matters where it's launched from, but if we're assuming it's launched from the ground, then yes. The vertical component of the velocity is equal to 0. The vertical component of velocity, that's true. The vertical component of velocity, that is true. But the total velocity is not 0. So number 10 is A. Number 11, a mass is attached to a spring with a spin constant K. If the mass is set into motion by displacement d from its equilibrium position, what will be the speed of the mass when it turns the equilibrium position? Okay, the equilibrium position, I'm going to use this as a diagram. The equilibrium position is when it's in its natural state and it's not moving. So it has not been pushed in and it has not been stretched out. Okay, it's just in the middle, it's not moving, that's what the equilibrium position is. Okay, so that's what the equilibrium position means. So then, if it's set into motion by displacement d, that's when we push it in and now we have a certain distance. Or maybe if it's another kind of a spring, we pull it out and it has a certain amount of distance. Okay, so the mass is attached to a spring with a spring constant K. If the mass is set into motion, what would be the speed of the mass when it returns to its equilibrium position? When you push it in, and then it starts going back and forth and back and forth and back and forth, the max velocity is there in the middle. Because you know it stops when it gets here, and then it speeds up, speeds up, speeds up, and then it stops when it gets here, and it speeds up, speeds up, speeds up. So the max velocity is in the middle. So that means that, like by our LOL chart, it started with no kinetic, but it did have potential. And then it changed over by the middle part. The potential is all gone. It's not stretched out at all, but it does have a lot of kinetic. And so I'm going to use this, and my U here is U sub S. So I'm going to use this formula, U sub S is equal to K, to solve my problem. The question is asking us to solve for speed. So I'm just going to do a little bit of algebra and solve for speed. So I need to divide by m. And so I divide by m, and then I take the square root of that because that's v squared. And I'm looking for this. I will say I use the x because that's what's in the formula. However, they use the letter D. So I really should change that over to a D instead. So as I look at my options, yikes. As I look at my options, I'm looking for a D here. And I have an X instead of a D. Well, I also know that, so I'm going to just highlight that for a second. That I'm looking at my X here, but it should be a D here, so I need to change that. The other thing is the square root of X squared, or D squared, is D, so that's why it's going to come out. Sorry, that phone call distracted me. When I took the square root, this is just V now, this is not V squared. So this is just a V. I'm going to go ahead and show the rest of this. So this was now KD squared over M, and so that's a V equals square root of D squared is D K over M. Okay. So it took a little bit of time to go through that algebraically, but I did finally come up with an answer, and that does match answer B. Okay, from the top of a high cliff, a ball is thrown horizontally with initial speed of v sub o. All right, it does have an initial speed. So as I look at my options, it can't be these because it's not starting at 0. It's starting with an initial speed. Which of the following graphs best represents the ball's kinetic energy as a function of time? Okay, so kinetic energy is 1/2 mv squared. That v squared tells me that it is a quadratic. It has a parabolic shape, and so this is the correct answer. 16 and 17. A block oscillates without friction on the end of a spring as shown. The minimum and maximum lengths of the spring as it oscillates are x min and x max. The graphs below can represent quantities associated with oscillation of functions of the length x of the spring. Okay, so just like before, this is the equilibrium position. If I pushed in here, it's going to bounce out and bounce and bounce and bounce and bounce and bounce so far. So it's just going to continually go back and forth. Which graph can represent the total mechanical energy of the block spring system? Notice, let's take a look at the graphs. They do have things on their x-axes, but they don't have anything on the y-axis. So they're kind of using these same graphs to describe each one. So the first one is asking about, what if this was total mechanical energy? So we'll just say total mechanical energy. All right. Total mechanical energy stays the same. We saw that in the energy skate park that we did. The energy stays the same. Whether it's potential or gravitational, it's going to add up to the same amount every time. So that has to be D. The next one, which one can represent the kinetic energy of the block as a function of x? And we mentioned a minute ago that needs to be parabolic. So it's neither one of these. It has to be one of these. And we have to think about, okay, just like a second ago, let's go back and read. X min and X max, so at X min it stops and turns around, and X max it stops and turns around. So at the max points it is stopped, it is 0. And so this one's going to match that. In the equilibrium, the middle position is when its max velocity is, and if it has max velocity, it has max kinetic energy. Okay, last two questions, 18 and 19. A ball swings freely back and forth in an arc from point 1 to point 4, as shown. Point 2 is the lowest point in the path. Point 3 is located 1/2 meter above number 2, and point 4 is 1 meter above point 2. All right, so we have a 1 meter difference in length, in height, and point 3 is halfway up there. If the potential energy is 0 at point 2, all right, well, let's think about this. If height equals 0, then potential energy is also equal to 0. Where will the kinetic and potential energies of the ball be equal? We've talked about this a couple of times, but because it is mgh for the gravitational, and then the total adds up, if we have half the height, then that's going to give me half of the energy here, and if I have half of the energy here, then the other half must be taken up by the kinetic, and therefore they are equal. So when it's halfway up, that is at point 3, they should be equal to each other. The next question, number 19, the speed of the ball at point 2 is most nearly what? Okay, so once again, down here it has no potential energy, but it has all kinetic energy. Up here it has all potential energy and no kinetic energy. So therefore we can use this setup. Okay, we're just going to take a second to solve this. Remember, when we solve it, we can cross out the mass, and we can multiply times 2, and then we can take the square root, and so we get this answer. Okay, well now we need to actually do some math. What does it have for us? Well, we know, let's just plug this in. We know gravity is 10. We know the height at point 2 is, it's the max point. So we're going to plug in a 1 because that was the max height that it reached was 1. So we're going to plug in a 1 there. So we really are taking the square root of 20. And if I go to my calculator and I take the square root of 20, I get 4.47, Oops, 4.47. And that is option B. All right, that wraps up the multiple choice. I hope this helps. If you need more help, feel free to come in during seminar. The other videos that are posted will be on the free response.